Un Univariate trees. In a univariate tree, in each internal node, the tester uses only one of the input dimensions. If the used input dimension xj is discrete, taking one of n possible values, the decision node checks the value of xj and takes the corresponding branch, implementing an n-way split. For example, if an attribute is color, which is chosen among the set red, blue, green, then a node on that attribute has three branches, each one corresponding to one of the three possible values of the attribute. A decision node has discrete branches and a numerical input should be discretized. If xj is numerical ordered, the test is a comparison, that is, fm of x, such that xj is greater than wm0, where wm0 is a suitably chosen threshold value. The decision node divides the input space into two, Lm, which is equal to the set x such that xj is greater than wm0, and Rm, the set of x such that xj is less than or equal to wm0. This is called a binary split. Successive decision nodes on the path from the root to the leaf further divide these into two using other attributes and generating splits orthogonal to each other. The leaf node define hyperrectangles in input space. See figure 9.1. Tree induction is the construction of the tree given a training sample. For a given training set, there exist many trees that code it with no error, and for simplicity, we are interested in finding the smallest among them, where tree size is measured as the number of nodes in the tree and the complexity of the decision nodes. Finding the smallest tree is incomplete. Quinlan 1986, and we are forced to use local search procedures based on heuristics that give reasonable trees in a reasonable time. Tree learning algorithms are greedy and at each step, starting at the root with the complete training data, we look for the best split. This splits the training data into 2 or n, depending on whether the chosen attribute is numerical or discrete. We then continue splitting recursively with the corresponding subset until we do not need to split anymore, at which point a leaf node is created and labeled. Classification trees. In the case of a decision tree, for classification, namely the classification tree, the goodness of a split is quantified by an impurity measure. A split is pure if after the split for all branches, all the instances choosing a branch belong to the same class. Let us say for node M, Nm is the number of training instances reaching node M. For the root node, it is n, nm to the I of nm belong to class Ci, with the summations of nm to the I, summing for index I, is equals to nm. Given that an instance reaches node m, the estimate for the probability of class Ci is p hat of Ci conditioning on xm, which is, by definition, as follows. P hat of Ci conditioning on xm is equals to pm to the I minus nm to the I divided by nm. Node m is pure if pm to the I for all I are either 0 or 1. It is 0 when none of the instances reaching node m are of class Ci, and it is 1 if all such instances are of Ci. If the split is pure, we do not need to split any further, and can add a leaf node labeled with a class for which pm to the I is 1. One possible function to measure impurity is entropy. Quinlan 1986, see figure 9.2. That is, Lm is equals to minus of the summations of pm to the I times log base 2 of pm to the I summing for all index I starting from 1 to k, where 0 log 0 is 0. By definition, entropy in information theory specifies the minimum number of bits needed to encode the class code of an instance. in a two-class problem if p to the 1 is equals to 1 and p to the 2 is equals to 0. All examples are of c to the 1 and we do not need to send anything and the entropy is 0. If p to the 1 is equals to p to the 2 is equals to half, we needed to send a bit to signal one of the two cases and the entropy is 1. In between these two extremes, we can devise codes and use less than a bit per message by having shorter codes for the more likely class and longer codes for the less likely. When there are k greater than 2 classes, the same discussion holds, and the largest entropy is log base 2 of k, where p to the I is 1 over k. But entropy is not the only possible measure. For a two-class problem where p to the 1 is defined as p and p to the 2 is equals to 1 minus p, phi of p 1 minus p is a non-negative function measuring the impurity of a split if it satisfies the following properties. Okay, there are several cases that can be described as follows. Phi of 1 half is greater than or equals to phi of p 1 minus p for any p which is chosen between the closed interval between 0 and 1. And phi of 0, 1 is equals to phi of 1, 0 is equals to 0. And phi of p 1 minus p is increasing in p on the closed interval between 0 and 1 half and decreasing in p on the 1 half and 1, the closed interval between 1 half and 1. And examples are listed as follows. 1 entropy, phi of p 1 minus p is equals to minus p log base 2 of p minus p times log base 2 of 1 minus p. Equation 9.3 is the generalization to k greater than 2 classes. 2. Gini index. This is Bryman proposed in 1984. Phi of p 1 minus p is equals to 2 times p times 1 minus p. And the phi of p 1 minus p is equals to 1 minus the maxima chosen among p and also 1 minus p, the larger one. And this can be generalized to k greater than 2 classes. And the classification error can be generalized to minimal risk given a loss function exercise 1. Research has shown that there is not a significant difference between these three measures. If node M is not pure, then the instance should be split to decrease impurity. And there are multiple possible attributes on which we can split. For a numerical attribute, multiple split positions are possible. Among all, we look for a split that minimizes impurity after the split because we want to generate the smallest tree. If the subsets after the splits are closer to pure, fewer splits, if any, will be needed afterwards. Of course, this is locally appeal, and we have no guarantee of finding the smallest decision tree. Let us say at node M, NMJ of NM take branch J. These are x to the t for which the test fm of x to the t returns outcome J. For a discrete attribute with n values, there are n outcomes. And for numerical attributes, there are 2 outcomes, n equals to 2, in either case satisfying the summations of nmj, summing for all j starting from 1 to n, which is equals to nm. Nmj to the ji of nmj belong to class ci, that is the summations of nmj to the I, summing for all index I starting from 1 to k, is equals to nmj. Similarly, the summations of nmj to the I, summing for all j starting from 1 to n is equals to nm to the I. Then, given that at node m the test returns outcome j, the estimate for the probability of class ci is as follows. P hat of ci conditional xmj is defined as pmj to the I, which is equals to nmj to the I divided by nmj, and the total impurity after the split is given as Lm prime is equals to minus of the summations of nmj divided by nm, summing with j starting from 1 to n, then with some inner summation. Sigma pmj to the I times log base 2 of pmj to the I, summing for all index I starting from 1 to k. In the case of a numerical attribute, to be able to calculate pmj to the I using equation 9.1, we also need to know wm0 for that node. There are nm-1 possible wm0 between nm data points. We do not need to test for all possibly infinite points. It is enough to test, for example, at halfway between points. Note also that the best split is always between adjacent points belonging to different classes, so we try them, and the best in terms of purity is taken for the purity of the attributes. In the case of a discrete attribute, no such iteration is necessary. So for all attributes, discrete and numerical, and for numerical attributes for all positions, we calculate the impurity and choose the one that has the minimal entropy, for example, as measured by equation 9.8. Then tree construction continues recursively and in parallel for all the branches that are not pure until all are pure. This is the basis of the classification and regression tree CRT algorithm, ID3 algorithm, and its extension C4.5. The pseudocode of the algorithm is given in figure 9.3. It can also be said that at each step during tree construction, we choose the split that causes the largest decrease in impurity, which is the difference between the impurity of data reaching node M, equation 9.3, and the total entropy of data reaching its branches after the split, equation 9.8. One problem is that such splitting favors attributes with many values. When there are many values, there are many branches, and the impurity can be much less. For example, if we take training index t as an attribute, the impurity measure will choose that because then the impurity of each branch is 0, although it is not a reasonable feature. Nodes with many branches are complex and go against our data of splitting class discriminants into simple decisions. Methods have been proposed to penalize such attributes and to balance the impurity drop and the branching factor. When there is noise growing the tree until it is purest, we may grow a very large tree and it overfits. For example, consider the case of a mislabeled instance amid a group of correctly labeled instances. To alleviate such overfitting, tree construction ends when nodes become pure enough, namely a subset of data is not split further if L is less than theta 1. This implies that we do not require that pmj to the I be exactly 0 or 1 but close enough with the threshold theta p. In such a case, a leaf node is created and is labeled with the class having the highest pmj to the I. Theta L or theta p is the complexity parameter, like h or k of nonparametric estimation. When they are small, the variance is high, and the tree grows large to reflect the training set accurately. And when they are large, variance is lower, and a smaller tree roughly represents the training set, and may have large bias. The ideal value depends on the cost of a misclassification as well as the costs of memory in a computation. It is generally advised that in a leaf one stores the posterior probabilities of classes instead of labeling the leaf with the class having the highest posterior. These probabilities may be required in later steps, for example, in calculating risks. Note that we do not need to store the instances reaching the node or the exact counts, just the ratios suffice. Regression trees. A regression tree is constructed in almost the same manner as a classification tree, except that the impurity measure that is appropriated for classification is replaced by a measure appropriated for regression. Let us say for node M, xm, is the subset of X reaching node M. Namely, it is the set of all X in X satisfying all the conditions in the decision nodes on the path from the root until node M. We define Bm of X is equals to 1 if X is in Xm. X reaches node M. Or Bm of X is equals to 0 otherwise. In regression, the goodness of a split is measured by the mean square error from the estimated value. Let us say Gm is the estimated value in node M. That is, Em is equals to 1 over Nm, summing for all r to the t minus Gm to the square times Bm of x to the t, summing for all in xt, where Nm is equals to the absolute values of Xm, which is equals to the summations of Bm of x to the t summing for all t. In a node, we use the mean, median if there's too much noise, of the required outputs of instances reaching the node. That is Gm of the summations of Bm of x to the t times r to the t summing for all in xt, divided by the summations of Bm of x to the t summing for all t. Then equation 9.10 corresponds to the variance at M. If at the node the error is acceptable, that is Em is less than theta r, then a leaf node is created and it stores the Gm value, just like the regression of chapter 8. This creates a piecewise constant approximation with discontinuities at leaf boundaries. If the error is not acceptable, data reaching node M is split further such that the sum of the errors in the branches is minimal. As in classification, at each node, we look for the attribute and split thresholds for a numerical attribute that minimizes the error, and then we continue recursively. Let us define xmj as the subset of xm taking branch j, that is the unions of xmj, union for all j starting from 1 to n, is equals to xm. We define bmj of x is equals to 1 if x is in xmj, such that x reaches node m and takes branch j. Bmj of x is equal to 0 otherwise. Gmj is the estimated value in branch j of node m. Gmj is equal to the summations of Bmj of x to the t times r to the t summing for index t, then divided by the summations of Bmj of x to the t summing for index t. And the error after the split is em prime, which is equals to 1 over nm, with the doubling summation, summing j and summing t of the term r to the t minus gmj to the square, then times bmj of x to the t. The drop in error for any split is given as the difference between equation 9.10 and equation 9.14. We look for the split such that this drop is a maximum or equivalently where equation 9.14 takes its minima. The code given in figure 9.3 can be adapted to training a regression tree by replacing entropy calculations with mean square error and class labels with averages. Mean square error is one possible error function. Another is worst possible error, em of doubling maxima, where the maxima is taken for oj and for ot of r to the t minus gmj, whose absolute value times bm of x to the t, and using this we can guarantee that the error for any instance is never larger than a given threshold. The acceptable error threshold is the complexity parameter. When it is small, we generate large trees and risk overfitting. When it is large, we underfit and smooth too much. See figures 9.4 and 9.5. Similar to going from running mean to running line in a non-parametric regression, instead of taking an average at a leaf that implements a constant fit, we can also do a linear regression fit over the instances choosing the leaf gm of x is equal to wm to the transpose times x plus wm0. This makes the estimates in a leaf dependent on x and generates smaller trees, but there is the expense of extra computation at a leaf node.